All right, we're going to look at some carbonyl-containing compounds now. We'll look at nitriles, that carbon-nitrogen triple bond, and then we'll wrap up this day of lectures by doing some practice problems with IR interpretation. So let's take a look at what a typical ketone looks like. So with a ketone, we have a carbon-oxygen double bond. We would expect to see that around 1700. And notice what else we have in this structure is our typical sp3 carbon hydrogen. If I ask you, well, do I have any carbon-carbon double bonds? Well, nothing there between 1500 to below 1700. There's no carbon-carbon triple bonds. There's no other types of hydrogen groups. You might say, what the heck is this thing? That's just, it's not strong enough to be any sort of signal. Don't misinterpret that. And it's just probably something unique to this compound. And you look at this and say, well, what about all this other stuff here? Don't need to worry about interpreting it. And one of the things I want to highlight is how do I tell the difference between something like a ketone and, say, an aldehyde? So I want you to take a close look at those two. And in your mind, or maybe kind of shout it out at your computer screen right now, what is the main functional group difference between a ketone and an aldehyde? In an aldehyde here, I'm going to have an sp2 hybridized carbon that's also bonded to a hydrogen. But for an aldehyde, it's in a weird place. How do I know I have an aldehyde? Because the sp2 carbon hydrogen of an aldehyde is going to show up in a region that regular other sp2 carbon hydrogens don't show up. They show up at around 2700 inverse centimeters. And again, how do I know that I got this aldehyde? I should see a carbonyl at around 1700. So I'm combining these two pieces of information here to tell me that I have an aldehyde as a functional group. If there was an sp2 signal past 3000 right there, that refers to an sp2 carbon hydrogen. I don't see that here, so I probably don't have any double bonds. And again, there's no carbon-carbon double bonds or no carbon-carbon triple bonds. And so that's one of the major ways, or that's kind of the only way to distinguish between an aldehyde and a ketone. All right, and then finally, last functional group I want to look at are nitriles. So a carbon-nitrogen triple bond. The big way that we know we have something like that is because it's going to be in our triple bond region. So very similar to where we would find a carbon-carbon triple bond. So this is why, as I've said in the past, it's advantageous for you to break this up into regions. So you have your hydrogen region, so anything bonded to hydrogen. Then you got your triple bond region, and then you got your double bond region. All right, so what I encourage you to do is pause the video, because I'm going to go through some examples now. Pause the video, go back, study, memorize your absorptions for the common functional groups, and then come back and let's try to do these problems. Okay, so let's take a look at this first one. So according to this IR, which of the types of bonds listed um, do these numbers correspond to? Okay, so let's just start with number one. I always like to start at the hydrogen region. I have a very large, broad signal here. Okay, that can really only mean one type of hydrogen group, and that's an OH bond. Then I got this signal here right below 3000. So again, that typically only means one type of group, and that's an sp3 carbon hydrogen signal. And then I look at the last one. So if this is 1500, 1600, 1700, there's a signal there. Now that's in my double bond region. How do I know if it's a carbon-carbon double bond or carbon-oxygen double bond? Well, at around 1700 is when the carbon-oxygen double bond starts. So that is going to be um, a carbon-oxygen double bond. Now, the next problem on the page is going to kind of have us pick out, based off of what we wrote here, pick out the structure of the compound, which is pretty much the only way we could actually do any structure relationships with IR is if we have a list to look at. So let's kind of take a look at that list here. And so which of these is consistent with the IR that's shown? So again, I'm just going to draw in what I put down on the previous page. That's an OH, that's an sp3 carbon hydrogen, and that's a carbon oxygen double bond. Now, before I look at the choices there, how do I know that this is not a carboxylic acid? Because I have both a carbon oxygen double bond and I have an OH. You look at the possible choices down there, like, wait, I don't see a carboxylic acid. Is this a typo? Remember that the OH of a carboxylic acid is going to kind of obliterate all of this. OHs of alcohols, as I said, stay in their own lane. So really what we're going to treat this as is a compound that has both a carbon oxygen and somewhere else an OH, but not a carboxylic acid. So look at my possible choices. That really only fits letter A. It's got the OH, it's got the carbon oxygen double bond, and it's got plenty of sp3 carbon hydrogens. Now, let me go through the other ones and just kind of highlight why the B, C, and D don't work. If we look at B, there's a carbon-carbon double bond. I should expect to see that somewhere between 1500 and below 1700. I don't see that. Well, how about a carbon-carbon triple bond, like in C? Well, I should see that somewhere between 2000 and 2500. I don't see that. And an NH group, those hydrogens, that's not a broad signal. Let me go back a little bit in the notes to find the NH2. So yeah, so look at here what that NH signal looks like. They're pretty sharp. Okay, the only thing that's really super broad are those OH groups. All right, so we could say the same thing for D. And again, like before, we can't have a carbon-carbon double bond because there is no signal for that. So really, as I said before, the only way we can really like pick out a structure from IR is if we have a list and we correctly identify the various the functional groups that the IR describes. Okay, so in this one, again, we're going to do something very similar, is identify the major functional groups, and then from that, pick out the right structure. So let's just identify what we see here. So I'm going to start in my hydrogen region. Right Above 3,000, there's a clump of signals. Right below 3,000, there's a clump of signals. So I know that this one is going to be an sp2 carbon hydrogen, and this is going to be an sp3 carbon hydrogen. Okay, so that's all I see in my hydrogen region. Do I see anything in the triple bond region? Yeah, nothing in the triple bond region. No carbon-carbons or carbon-nitrogen triple bonds. Now I'm going to go to my double bond region. I see some signals there, like right above 1,500 to about 1,600. What do you think those represent? Those are carbon-carbon double bonds. And, maybe these here represent the combination bands. Maybe there's a benzene ring. So let's just kind of put together what we think are as a possibility. Think that benzene is there. It's got to have sp3 carbons and then no carbon oxygen double bonds. So do you see any of those choices that have those functional groups present? Well, the only one that really kind of fits that is B, because we have benzene, we have sp3 carbons, and there's no carbonyls in this. Now you look at that and say, well, wait a second, there's a nitrogen there. Like, shouldn't there be an NH bond? Well, look at that type of nitrogen. Remember, nitrogen's happy with three single bonds to it, six bonding electrons, and one lone pair. So there's no NH bond, and that's fine. It just means I won't see it here in the IR, and that's okay. In fact, that's a kind of good hint. Like if you think you have a nitrogen present, yet you don't see any NH bonds, then you know what kind of nitrogen you have. There's a nitrogen that does not have any hydrogens on it. Now let's try to go through and look at like, for example, A and try to see, well, why is A not the right answer? Well, A's got NH bonds in it, so I should see NH signals, which I don't. Why isn't C correct? Well, C's got a carbonyl, which the IR says I don't have, and NH bonds. And then I could say the same thing for D. There's NH bonds present and a carbonyl, which is not showing up in the IR. And then finally, let's look at one more problem. So again, same possible answers, but let's see if we can find a different result here. So now I go to my hydrogen region. All right, notice I got a couple sharp peaks here, around 3,300-ish or so. That's where my NHs are going to be. And notice how I have two of them. So I should have an NH2. I have sp3 carbon hydrogens present. No triple bonds. So I'm going to go now to my double bond region. And right there, really close to 1,700, is going to be that carbon-oxygen double bond. So let's kind of pick out some possibilities here that have all of those things. I'm going to eliminate B because that does not have a carbonyl in it, nor it does the nitrogen in choice B doesn't have any hydrogens on it, so that wouldn't work. I'm going to eliminate D because there's sp2 carbon hydrogens on D, and I didn't see any in the IR. And now this leads me to A versus C. So the big difference between A and C is A has got a carbon-carbon double bond. C has a carbon-oxygen double bond. Which one did I say was present? The carbon-oxygen double bond. So my answer for this problem is going to be C. So this is kind of the extent that we're going to take IR spectroscopy. The main thing that I want you to be able to do is look at an IR spectra and tell me what functional groups are present. Because we're going to use IR spectra with other forms of spectroscopy, specifically NMR spectroscopy, to come up with the structure of a molecule. And this will be much like a puzzle. This will be one piece that we use to put together with a whole lot of other pieces to get the big picture on what a molecule looks like.